rational functions, and I wanted to just give you an overview of what the difference is and the definition. 3.1 is going to be on quadratics, which is a type of polynomial graph. 3.2 and 3.3 are going to help us figure out the zeros of polynomials. 3.4, we're going to put together all that we've learned and just graph any type of polynomial expression or function. And then 3.5, we're going to shift gears, and that's the part of it that's called the rational functions. So actually, it seems strange to me whenever I say that, because this is quite a meaty section all to itself, but it's crammed into one section. Whatever you do, don't be absent that day, right? If I came back after missing 3.5, I would think, what in the world? So there's a whole bunch of kind of different types of things in that section, rules for us to follow and so on. So I'll try and make sure I have the video of it though, so something would come up. But anyway, that was kind of oddball section. These others kind of go together. They're all about the polynomial function. So I wanted to show you, in your notes it says the definition for a polynomial function is of degree n, where n is a non-negative integer. And then it describes it like this: f of x equals. And it has this crazy looking algebra definition, and I want to talk to you about that. And it says where a sub n minus 1, dot, 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 a sub 1, and a sub 0 are real numbers. So it's really just telling you these coefficients. It can be anything. It can be 7 or 2 or negative 5 or square root of 2. Any real number can set in front of that, except a sub n cannot be 0. So that's how it's defining it algebraically. And then x to the n, it says n, where n is a non-negative integer. So n has to be a non-negative integer, which I would call the whole numbers. So like 7, 8, 0, 2. These are positive or non-negative, so we catch 0 in there. Non-negative integers. All right, so I wanted to talk to you because I had this thought where Cheney and I have been setting through the calculus lectures, and we've been listening to Herb from MIT from the 1970s explain calculus to us, and it's been real interesting. And he said something on his video the other day that I thought was good. He said the math book is written like this because it has to be very specific. It's a universal language. So whether you're in India or China or America, South America, and you're reading your textbook, that it can be interpreted the same way. So it's a universal language. There's no misunderstanding this. And he compared it to writing up some sort of lawyer language. You know, when you read a contract, it's so confusing, and you think, what in the world? And they have this and that and everything. And he says it's the same thing whenever you write a contract. It has to be so specific that there's no misunderstanding. For example, whenever I write a syllabus for the department, whenever we're trying to come up with all the rules that we're going to follow for, say, Math 120, and I coordinate that, everybody has their input and what they want the rules to be on the way you take the exams and the way the grades are figured. And every time I write it down in my Cindy language, then I go back and read it, and then we're like, well, someone could think you meant this when you said that. You need to be more clear, and you need to say this clause and that clause. So anyway, by the time you get it written so that it's absolutely no mistaking what you mean, it sounds pretty complicated. And sometimes that's how our math book looks. But the reason for it is just so it will be a universal language. So no matter who you are, where you are, it means the same thing if you dig deep enough into it. And that kind of gave me peace about it. I thought, yeah, that's a good thing. You want it to be absolutely unmistakable, the rule for everybody the same. Anyway, in Cindy language, the way I would say this is polynomials are like this. Examples. It would be polynomials have your variable raised to different whole number exponents, like this is x to the first, and then the constant counts as being with x to the 0 power, which it counts as a polynomial. It can be raised to the 0. So constants have your variable raised to the 0 power, and then this x is raised to the first, and the coefficients are just real numbers. So a linear equation is a polynomial function. We learned how to graph that. Y equals, by going to the y-intercept, rise 3, run 1, that's a polynomial function. Another example, again to the first power, all linear equations are polynomial functions. They're first degree equations. So this, we start at 1, the y-intercept, rise 5, run 1. Another polynomial expression. And yet another one, in case we want to just make sure we saw that. Anytime it's solved for y, you see the slope and the y-intercept. So we start at the y-intercept, -3, rise -2, run 1, that's a negative slope. All right, so anyway, I just wanted you to absolutely know linear equations fall under this category as polynomial functions. Today, our focus is going to be on the quadratic, x squared. Any second degree polynomial is going to make a U shape every time. So our basic one, x squared, looks like that. Then we talked about the shifting rules in a previous lesson. If you have something grouped with x, that's the left-right shift. So the parabolas move back 1, and that's the vertical shift down 1. So back 1, down 1. It's positive and a little thinner. The 2 makes the graph a little more narrow. If I wanted to be more specific, I would need to plot some points, plug in something for x. You have to do that in some of your homework to get the curve to draw in on Math Excel. But that's kind of the general sketch. All right, so that is a polynomial function, x raised to the second power. Also, x raised to the third power, we've studied it, it's x cubed graph. Another example, here's the polynomial in its factored form. But I wanted you to know if that were multiplied together, I FOILed that and then times it by x plus 7. Multiplied together, that is a third degree polynomial. Third degree polynomial. Remember, polynomial just means the exponents are whole numbers. So, you know, what isn't a polynomial? We need to do some examples of that in a minute. But our focus is mainly what is a polynomial, things that have our exponents that are whole numbers. So x to the third, it has an x2 and an x1 and a constant. So it's in that descending order of the general rule. But what determines its degree is that biggest exponent. So where it's third degree, that tells me that the curve is going to have possibly 3 solutions. Remember, your biggest exponent determines how many solutions you can have. Linear equations have 1 solution. Quadratics can have 2. We find that in the quadratic equation. Third degree can have 3 solutions. Up to 3 solutions. Now this one, x to the third, only had 1 solution. And it just crossed the x-axis in one place. What I want you to see in this lesson is that solutions are x-intercepts in the graphing world. How you find what we're calling a solution or an x-intercept is by setting y equal to 0. So if I were to make this, f of x is y, make that a 0, and then try to solve this equation, I don't know how to solve third degree equations because they're usually not factorable just off the top of my head. I can't use a quadratic formula. They're harder to solve. So hopefully a lot of your homework will be in factored form. So you'll be able to use that to find your solutions. So in this form, if it's already factored, you set y equal to 0. Then to solve, if it's in factored form, you set each factor equal to 0. So x minus 1 equal to 0, x plus 2. That's the 0 factor property that allows that. We've done that in our past. And then you get 3 solutions. X is 1, -2, and -7. And like I said, the solutions are actually x-intercepts. So here's my little sketch of the graph. I have an x-intercept at 1, at -2, and at -7. Okay, so that's going to be our big battle in section 2 and 3 when we come back next week. So we'll talk about how to find the zeros of the functions. Because sometimes it's not in factored form for us, and we'll use this synthetic division method to try to make it in factored form, to try to find out how we can divide it down a little bit. Anyway, when it's in this form, though, what I can readily see is that it is third degree, where you might not notice it as much in factored form, but if you multiply it together, you kind of think through it and see that is third degree. But here it's real obvious. Biggest exponent is 3. Another nice thing about this form, in its polynomial standard form, is the y-intercept is always the last number. If you were to plug in x is 0, and that is how you find a y-intercept in graphing. When x is 0, 0 times that, 0, it zeros all those x terms out, and the y-intercept's just setting at the end. It's the constant. So in this form only, if it's in expanded standard form, the y-intercept's at the end. So I've noted that on my little graph. The y-intercept is negative 14. So a complete sketch, and kind of getting ahead of ourselves as we're going to do this in section 3-4, is to find your x-intercepts, find the y-intercept, and then to sketch the graph by the end behavior. End behavior, I want you to note this. If it is third degree, the ends go different directions. The final ends of the graphs split apart. Notice it on this x third, you've got one end down and one end up. The regular basic x in the third splits apart. X to the first, our lines go different directions. If it's a negative slope, the left side is up and the right side is down. If it's a positive slope, it goes negative, low to high. Okay, second degree polynomials, or any even degree polynomial, the ends will go together, like our parabola. X squared, if it's positive, it's up and up. And then if it's negative, it's down and down, but the ends go together. So those will be our polynomial rules. And that will really, if you get a head start on your homework there, that's really it in a nutshell. Find your x-intercepts by finding how to factor that, which we'll have to battle through that a little bit in the next two sections. The y-intercept and the end behavior, and then sketch it in. All right, so now let me tell you the other part of the story, what's a rational function, where we're just kind of overviewing where we're going with this. So if this is a polynomial function, we have whole number exponents, and not a polynomial function would be things that aren't whole number exponents. So maybe your negatives, like f of x equals x to the negative 1. If your exponent is negative, that makes a fraction. That would be y equals 1 over x graph. And that's actually our rational function. That's our basic 1 over x graph. It looks like that. And that's what we're going to do on that last section. We're going to learn all the rules about how to find the asymptotes, or the lines that you guide in to draw this, because it has breaks in the graph where you have the fraction, the variable, and the denominator. So that's one example of not a polynomial. That's rational. Another example would be if you had f of x equals x to a fraction. A fractional exponent, those don't count as integers, or whole numbers, I should say. A fractional exponent is a radical. So radicals are not a polynomial. Square root of x looks like this. All right, if you have a true polynomial function, the nice thing about a polynomial function is they're smooth and connected. From left to right, the graph flows. You never pick up your pencil. There's no breaks in the graph. It doesn't stop some certain spot. It goes on to the left, on to the right. So all of your polynomial functions will have a domain. Polynomial functions have a domain of negative infinity to positive infinity. They're smooth and connected. Continuous. Smooth, connected, continuous graphs. So you flow from left to right. Point to point has to connect.